Chapter 2, Energy Transfer, and General Energy Analysis. So in this chapter, we begin our understanding of how to compute the energy of a system. So there's different forms of energy. So we'll start with the very basic ones. First, as you learned back in university or general physics, you have kinetic energy, you have potential energy. Those are the two big types. When our book, instead of using the SI unit of joule, we're going to use the kilojoule because um, we're dealing with typically large amounts of energy. So our book and uses kilojoules for energy. So the equation is the same, 1/2 mv squared, but it's uh, typically m will be in kilograms here. Um, Now we do define what's known as the kinetic energy per unit mass, which is simply the top formula divided by m. This is very useful because oftentimes we're dealing with a fluid, and so we're dealing with a flow rate. We don't specifically know how much mass we have because it's a flowing liquid. So it's more common to use the flow rate because you can measure flow rate with an instrument. Similarly, we define the potential energy as mgz. Again, notice this is in kilojoules, this is the preferred unit. So we can define what's known as the potential energy per unit mass as the potential energy divided by mass. So that makes the total energy of a system equal to the following equation. You have U, which is the internal energy of a system, plus the kinetic energy, plus the potential energy. Um, we can define the energy per unit mass as this equation divided by m. So here U would be the internal energy per unit mass, kinetic energy per unit mass, potential energy per unit mass. So there's an easy relationship between the capital E, the total energy, and the energy per unit mass given by the equation here. It's big E divided by m is small e. When we're dealing with fluids, we need to understand the relationship between mass flow rate through a pipe. So here we have a standard kind of pipe. This shows a cross section of the pipe. It has a diameter d. The area of the pipe is pi r squared. So our book likes to use the diameter here because the problem's often given in diameter. What I like to use is these two equations here. The area is pi r squared because it's a circle, and the diameter is 2 times the radius. So if you take this equation for D and you solve it for R and you plug it in the top equation for A, you end up with this equation here. You can use either sets of equations. You can use the equation for the diameter, or you can use these two equations, depending on how the problem is given. So we have a flow rate through a pipe. The mass flow rate, so this m dot, so this is kilograms per second, a mass flow rate, is given by the density times the area of the pipe times the average velocity of the flow. Uh, you can also rearrange this a little bit. You can write this same equation as the density times the volume flow rate if you work out the units. Uh, so either one of these is sufficient. And so it's kind of hard in our book to keep track of this script looking kind of V and this V here. And so what I did over on the side is I put what these are. So the script V with a dot, that is a volume flow rate, cubic meters per second. Rho is the density, that'd be kilograms per cubic meter. V is the velocity, so that's meters per second. So again, depending on how the problem is stated, you have to use this equation or that equation. This I kind of keep track of what these different V's are. They're different. So once you have the mass flow rate, you can multiply by the energy per unit mass to find the energy flow rate. So this would be in kilojoules per second, which is a kilowatt. So if we have a solid object, like typically you dealt with back in your elementary physics classes, it was pretty easy to calculate the total energy because the total energy was the sum of kinetic energy plus the potential energy. Our systems we deal with typically aren't solid objects, they're fluids. And so, uh, you have a fluid going through a turbine, through a pump or a fan. Uh, so each of those devices actually changes the mechanical energy by either raising its pressure or lowering its pressure. So our book goes through an analysis and shows that uh, you have the kinetic energy term, and you also have the potential energy term, but you also have a term that's added to the energy due to the change in pressure. So the book develops the formula for the total energy of a fluid uh, per unit mass as the pressure divided by the density plus uh, the kinetic energy term plus the potential energy term. So this equation will be pretty vital to us as we move forward. So in summary, here's what you have. You have the equation I showed on the last sheet, mechanical energy of a flowing fluid per unit mass. You have the total energy rate, which is just m dot times E mechanical. Um, if you have a change in, uh, say you have a fluid going through a turbine, you can have a change in mechanical energy. So therefore, it's the pressure difference over the density plus the change in kinetic energy plus the change in kinetic potential energy. And likely, you can also multiply this equation by m dot and get the rate of mechanical energy change. And this will be in kilowatts. So let's take a look at an example. This is example 2.2 out of the textbook. A site is evaluated for a wind farm, observed to have a steady winds at a speed of 8.5 meters per second. Determine the wind energy per unit mass for part A for a mass of 10 kilograms for part B, and for part C for a flow rate of 1,154 kilograms per second for air. So these are just direct applications of the formula. The kinetic energy per unit mass is v squared over 2. So here's your velocity squared divided by 2. Now this will come out in units. If you didn't have this conversion unit in here, it would come out in units of meters squared per second. But we want this in joules per kilogram because it's an energy per unit mass. And so conversion factor is 1 joule per kilogram is equal to 1 meter squared per second squared to get it into the right units. To find the total energy, we just have to multiply by m for part B, which is 10 kilograms. So that makes it 361 joules. For part C, we have a flow rate, mass flow rate. So here, we're going to use the formula here. E dot is m dot E. Since we know what m dot is, we just calculated E from part A. We can multiply this out, and again, the unit will come out in kilowatts, and so a conversion unit is 1 kilowatt is 1,000 joules per second. Because here, when you cancel the kilograms, you can't. Let me put the pencil on here, and let's see if I can do this for you. If you cancel this kilogram, will cancel this kilogram, and you'll be left with joules per second. A joule here and a second there will be left, and so then you can convert 1,000 joules per second is equal to 1 kilowatt. So that turns out to be 41.7 kilowatt. Oftentimes we're interested in hooking systems together, so we'll have energy transfer between systems. Heat is defined to be the form of energy that is transferred between two systems by virtue of a temperature difference. So if you have a temperature difference, those systems will tend to try to equalize themselves. So we also define what's known as a closed system or an open system. So the first slide here shows you what's known as a closed system. A closed system is where the mass is constant. However, the heat can transfer back and forth. You can also do work on a closed system. It's just the mass is constant. We'll look at an open system in the next slide where the mass can also change. So the diagram on the right here shows you that temperature difference is the driving force for heat transfer. If the room is at 25 degrees C and your soda is at 25 degrees C, well then they're in equilibrium. There's not going to be any transfer of heat between the room and the soda or vice versa. However, if your soda's at 15 degrees C, you have a 25-degree air temperature, you're going to have heat being transferred into the soda uh, until it reaches 25 degrees C. So you need 8 joules per second going in there, for example. Eventually, this thing will heat up to 25 degrees C. And of course, if the soda is at even colder temperature, there'll be even more heat transfer into the soda. I mean, the final result's going to be the same. The soda eventually gets to 25 degrees C if left long enough, but uh, the heat will initially start transferring in faster because the heat transfer rate is proportional to the difference between the room temperature and the soda. Um, so from the previous slide, if Q is the heat transfer in kilojoules, we can define the heat transfer per unit mass, small q, as big Q divided by M. And again, we'll have units of kilojoules per kilogram. Another term we often see is what's known as the heat transfer rate, which is the kilojoules per second, let's say. So if we know the heat transfer rate, we can multiply by the time to get capital Q. Again, that'll be in kilojoules. So the slide to the right here shows you sort of an example. So let's say we have a system. Here's our boundary. We have 30 kilojoules of heat coming into the system. So Q would be 30 kilojoules. Let's say there's 2 kilograms worth of stuff in here, and this heat transfer occurs over 5 seconds. So we can define Q dot as Q, 30 kilojoules divided by delta T of 5 seconds, we get 6 kilowatts. Small q will be big Q divided by M, so that'll be 30 divided by 2, or 15 kilojoules per kilogram. So we define heat as energy that is transferred across system boundaries. So for example, here if we have a baked potato, everything inside the baked potato is known as our system, if that's what we're interested in studying. Dividing the system from the surrounding area, we define what's known as a boundary, a system boundary. So once heat crosses through, energy crosses through that boundary, we define that as to be heat. And it can go either way. It can go out of the system or go into the system. Now, a special case is where we insulate around the system, shown in the figure right here. So this, say, inside of here is our system. If we insulate around the system such that no heat can flow across the boundary, that we define that as what's known as an adiabatic system. We'll come back to look at that later in future chapters. There are 3 different heat transfer mechanisms. Conduction is the transfer by particle by particle. So let's say you in the morning you get a cup of coffee, you pick up that's hot, you pick up a cold spoon, you put it in the coffee and you start stirring your coffee around. Heat will transfer from the coffee to the spoon via conduction, particle by particle. Another example is what's known as convection. Convection is the flow of heat by motion, fluid motion. So you either have to have water flow, air flow, or some other kind of fluid that's flowing. The last type is what's known as radiation. Radiation is the transfer due to the emission of electromagnetic waves. So there's a couple of examples of this. One is this is how the Earth gets its energy from the sun. That's the radiation. A lot of these kind of mechanisms, you can get heat transfer from an object via more than one of these at any given time. Our primary concern in the first part of the course here is going to be dealing with the conduction and convection. You can also transfer energy by doing work. So what is work? Work is the energy transfer associated with moving a force through a distance. So for example, a rising piston, a rotating shaft, electrical wire crossing system boundaries, all of these are associated with work interactions. So in our book has what's known as a sign convention for all forms of work and heat, because one, you have heat and work being transferred in and out of the system. So one way to do this is to treat heat to a system and work done by a system as positive, heat transfer from a system and work done on a system as negative. That's a little confusing, and our book uses what I think is a better method, is to use the subscripts in and out to indicate direction. I think this makes it a lot more clear. So for example, let's say we have a system. You can have heat being transferred into the system or out of the system. You can have work being done on the system or the system doing work on the surroundings. This makes it a lot easier, I think, to keep track of everything. So in our example here on the left, again, you have 30 kilojoules of work. The mass is 2 kilograms, and the time interval is 5 seconds. So here you have a case where the system is doing work on the surroundings. Notice this is work out. So W dot is just the work rate, which would be 30 kilojoules divided by 5 seconds, 6 kilowatts. Small w is the work per unit mass. That's going to be 30 kilojoules divided by 2 kilograms, or 15 kilojoules per kilogram. So what is the fundamental difference between heat and work, and how they differ and how they're related? So both heat and work are recognized at the boundaries of a system as they cross the boundaries. That is, both heat and work are what's known as boundary phenomena. So systems possess energy but do not possess heat or work. So this is a little bit confusing sometimes for students, but the systems you study, for example, if you have a glass of water, let's say, that glass of water has certain properties. It has a certain mass. It has a certain volume. Those are inherent to the system. Heat and work are really not associated with the system per se. They're associated by transferring from one state to a different state. So the author has a diagram in the book, and I've shown here on the slide. Let's say we have a system that's in state 1. Let's say this is a gas. It has a certain volume. It has 2 cubic meters and a certain pressure. Now he didn't show the pressure over here, but you could just come across to the left, and you could read. If this was tabulated, you could actually read what the pressure value was here. Let's say it's 1 atmosphere, for example. So we want to go from state 1 down to state 2. So notice the volume is different. The volume got a lot bigger. It's 5 cubic meters. And notice the pressure got lower. You come across to the left, and you'd have a different pressure. So the pressure at 1 is much higher than the pressure at 2 down here. So 1 and 2 are what's known as states. They have a certain pressure and a certain volume. If you go from state 1 to state 2, you can take many paths to get there, depending on how you change the system. Changing the system from one state to another state involves typically doing heat on it, adding heat, so taking away heat, doing work on it, or having the system do work. So these different ways to get from state 1 to state 2, what's known as paths. They're path functions is what they're called. The magnitudes depend on the path followed, from going from one state to another state. So let's talk about the different types of work you can do on the system. The next several slides go through specific examples with equations. The first type we look at is what's known as electrical work. So let's say we have a system, and outside, of course, we show our boundary here, and outside is the surroundings. One way we can do work on the system is through electrical means. We can have wires penetrating through the boundary, carrying a current through a resistor. So the power that we can put into a system across the boundary is simply I squared times R. You could back from your elementary physics equations. Of course, that's also equal to V squared times R, because we can use Ohm's law to relate the I squared R second equation to this third equation. If we know how much, once we have the power, if we know how much time it takes for this to occur, let's say it's delta t seconds, we can multiply the power, V times I times the rate at the time to find how much energy, and that'll be in kilojoules. There are also different kinds of mechanical forms of work we can do on the system. Uh, Basically, you have to have two things. You have to have a force acting on the boundary, and the boundary must be able to move. This goes back to, again, to your elementary physics days. If you have you exert a force on a mass, you move it through a distance, that's work, mechanical work, force times distance. Of course, if the force is not constant, you can also obviously integrate from point 1 to point 2 to figure out how much work you have there. Big thing is, for mechanical work, is if there's no movement, there's no work. A force has to actually cause the object to move, has to cause the boundary to move before you have mechanical work. Another kind of work you can have is what's known as shaft work. Again, because you can have a force moving through a moment arm, generating a torque. So a torque equals force times R. You can take this equation, solve it for F. Then you can calculate what's known as the shaft work. The force is the torque divided by R times the 2 pi R times N, with N is the number of turns it moves. So if you put these two equations together, you end up getting a nice equation, 2 pi N times the torque. If you know how fast this occurs, again, you can take this and you can divide by time. You can get the power transferred. That's equal to 2 pi n dot times t, where n dot is the turns rate. How many turns per second, for example, the shaft turns. So let's take a look at a simple example, example 2.7 out of the textbook. Determine the power transmitted through a shaft of a car when the torque is 200 Newton meters and the shaft rotates at 4,000 revolutions per minute. So we're going to use the formula that we had just developed, 2 pi times n dot. Well, n dot, we have to get this to the right units. So we want to convert from 4,000 revolutions per minute down to seconds. So we'll have 1 minute is 60 seconds. Then we can plug in the 200 Newton meters here for the torque, but we also want to convert Newton meters to kilojoules. So 1 kilojoule is 1,000 Newton meters. So what you have, putting all this together, is you have the Newton meters canceling. Let me get my pencil here working. This unit will cancel this unit. You have the minutes canceling the minutes. And what you'll be left with when all that is done is you'll be left with kilojoules per second, which is a kilowatt. So 2 pi times 4,000 times 200 divided by 60 times 1,000 will be 83.8 kilowatts. And if you want, you could convert that to horsepower, but that's a conversion in the back of the book. Another way we can do work on a system is through use of spring work. When a force is applied on a spring, the length of the spring changes. When the length of the spring changes by a amount dx, under the influence of a force F equals kx, this is known as Hooke's law, the work done can be determined by integrating the force through the distance moved, dx. Well, if you plug that in and do that, what you get for the work is you get, due to the spring, is 1/2 k. K is the spring constant, how the stiffness of the spring, times the x2 squared minus x1 squared, where x1 and x2 are the change in lengths, initial and final displacements of the spring. So let's take a look at example 2.9, power needs of a car to accelerate. Determine the power required to accelerate a 900 kilogram car as shown from rest to a velocity of 80 kilometers per hour in 20 seconds on a level road. So in this case, since it's a level road, we're not dealing with a change in potential energy, but we are dealing with a change in kinetic energy because the car goes from rest to 80 kilometers per hour. So here, all we need to do is calculate the change in kinetic energy, which is given by 1/2 m v final squared minus v initial squared. Well, v initial, v1 is 0, so that's pretty easy. We know what the mass is, it's 900 kilograms. We know what the final velocity is, it's 80 kilometers per hour. Now, one way to proceed here is simply to take the 80 kilometers per hour and convert it uh, to meters per second, and then plug it in the formula. Our book sort of doesn't do that. He tries to save a little typeface and put it all in one. So here you see, this is 1/2 times the mass. Uh, this is your V2, but he's written it as 80,000 meters. So that's the 80 kilometers divided by an hour, which is 3,600 seconds. So here he's doing the conversion here. Um, so when you square this out, you multiply this out. He wants to come out in kilojoules, so he puts this conversion factor on the end here. 1 kilojoule per kilogram is 1,000 meters squared per second squared. And again, you could do this conversion on a separate line if you wanted to as well. But once you found the work, you can divide by the time because it says it takes it 20 seconds. So we get 222 kilojoules divided by 20 seconds, 11.1 kilowatts.